Good morning, everyone. Do you have all of you your breakfast with you? So if you are ready, we can start. I would like to show you something interesting that is unfortunately very actual, and it is on a data set about all the data that can be found on the COVID-19. And there is a challenge on this data set, and I think it is very interesting because it is it's very well organized. There are a lot of questions, a lot of tasks that can be done. So I think that probably we can see something on this kind of data set to have something very actual in some lab sessions, or probably in some homework assignments. So here is a dataset description, and there are a lot of course, it is a challenge, so there is a prize, but for the course there is no prize, so I'm sorry. And but we can see some tasks among those described, and it's very interesting. So basically, they are problems of classification and regression and so on. So starting from the data, you should analyze the data and try to give an answer to these questions. So I think it is very interesting, and we can probably later make use of this data set. I would like to give you some knowledge, some recall about linear algebra, and in the meantime I will take this opportunity to take some practice on Python, implementing linear algebra structure and so on. And in the same time, I would like to take this opportunity to introduce some basic knowledge about signals, so how to deal with signals using Python and linear algebra. So you can also open Jupyter when you are ready. And meantime, I would like to tell you something about tensors. So what is a tensor? A tensor is a generalization of a matrix. So a tensor gives us a generic description of what is a multidimensional array with an arbitrary number of axes. So you can see as a tensor as a linear arrangement of a set of K matrices. So you can see a tensor as a collection of matrices, like this equation, in which you have a tensor which is denoted with a capital letter with some different font face in order to distinguish it from matrices. And it is a collection, a set of a linear arrangement of a set of matrices. So x1, x2, xk are matrices. It is a generalization of a matrix, since a tensor of two-dimensional tensor is a matrix. And it can be seen as stacking horizontal, vertical, or lateral slices. So tensors are very important with signals because they can represent three-dimensional signals like video signals, or a time frequency representation of signals. Or also higher dimensional signals like magnetic resonance images. in which you have different slices of your signal. So you have a four-dimensional view of an object. So you can have a lot of. So this is a typical representation of 3D tensors, but here is a 3D tensor, but you can have also higher dimensional tensors. So you can have a collection, for instance, of 3D tensors, and you can obtain something like this one. So this is just a graphical representation. So you can structure tensors as you need, and they are very important. So one of the main application, for instance, is when you need to work with color images. So yesterday we saw how to deal with black and white images in which we have just a matrix. Since we have just the luminance indication, the values of the luminance, so we can just arrange all the values in a matrix. For the color images, we need a three-dimensional tensor, because we need to store eight width and channels. So we need to have the values that can be stored for each channel, and for an image color we have 3 channels, so red, green, and blue. So in order to do that, we have a tensor. And we can see how to write a tensor in Jupyter. So I can go to my folder. Okay, so here I have the folder data, and I can create a new Python notebook. Okay. So how to deal with tensor? So again, you can write your, I don't know, some information as always. And I don't know your name and date of today. So we can write, so here we are talking about tensors. So we can write something on, we can write something, how to write a tensor in Python. So we can write something like this. So x, which is our structure, the variable in which we store our tensor. Of course, we need to import NumPy and as usual. So we need to import NumPy so we can write our tensor as a NumPy object. So I don't know, we can take, for instance, 24. So a number of elements that goes from 0 to 23. And we can reshape in a three-dimensional tensor, which has width of 2, so height of 2, width of 3, and a number of 4 of channels, so the third dimension. And we can see here is our tensor. It is written in this way, but of course, you can also reshape as you prefer. And so you can see that here is a stack of two matrices. But of course, you can have you can arrange your tensor as you prefer, of course, as you need. And so tensors are so you can apply any kind of things that we saw for matrices, so slicing and other things and so on, to tensors. And I would like to just directly show you something related to manipulation of signals with tensors. So how to manipulate signals with tensors. So we can take an example of how to store a color image. So in our folder data, we have a color image, and we can load this color image by using matplotlib library, as we saw yesterday. So we can, first of all, import matplotlib.image, and we can use it as PMG. So we can load our image. So emread, which is the command that read the image. So I don't remember the name of the image. So I go to folder data, and it is the baboon, I think. Okay, baboon. So data baboon.png. Okay, if you look at if you print the object EMG, the structure EMG, you can see a collection of numbers, a collection of matrices. And here is our tensor. If you want to know the dimension, the size of this tensor, you can look at the shape. So here you can see that you have a square image with 3 channels. So we have 520 elements for each matrix, for each channel. So a square matrix of 512 values for each channel. And you can now, of course, you can plot your image. You can emg plot equal to plt em show. So it is similar to show, but you need to write em show when it refers to images. PLT is not, because I didn't I didn't define the matplotlib at pyplot, so I need to define also pyplotlib. So I can add a cell here, or better here, and from matplotlib we can import pyplot as PLT. Okay, so we have plotted the figure. So we have the figure plotted in our image plotted in our figure. Of course, you can take some operation like the ones we saw yesterday for matrices or black and white images, just selecting, for instance, one channel. So, for instance, you can see here in I don't know, one. So you can see just select some one channel. So for instance, the first channel, so the red channel. So I take all the elements for the rows, all the elements for the columns, and the first channel, so index 0. And I can plot this image. I can choose a color map. If you remember from yesterday, we can choose, I don't know, something like summer. And here you have the same image with only one channel with this color map. Of course, you can have all the other color maps. If you write here gray, you can have the black and white, so the gray scale luminance. Okay, so here is. So this is when you select only the red channel. Of course, the image can change if you select the green channel, for instance, or for instance, if you select the blue channel. So you have different views depending on what is the channel that you are going to select, and have different color maps as you need. So this is viridis and so on. So it can be useful if you want to take evidence, if you want to highlight something rather than other in your image. I will go on and introduce some basic operations with tensors in general, but we mostly use matrices for the moment. So I will focus on matrices for the moment. Then when we will use lots of tensors, we may, but you have the same operations also for tensors and matrices. So we can start a new, I don't know, you can take some new title, for instance, basic operations. And we can start with the simplest operation, which are the operations that are called element-wise operations. So I would like to give you some concepts. So we can have, of course, addition and multiplication of matrices. If you addition of matrices is very trivial. So if you have two matrices, you can have their sum, the sum of the matrix as the sum of all the elements of the two matrices. So this is called an element-wise operation. So you just take every element from the matrix A and you sum the corresponding elements of the matrix B. And this is called element-wise operation. For matrices, we have different kind of multiplications. I will show you directly in Python. So for addition, we need to import. I don't remember if I have imported. Yeah, of course, NumPy at the beginning, so we can move every import at the beginning, so we can have a clear view at the beginning of all the library that I have imported. So we can move the cell in this way. So I have already imported NumPy, and we can work with NumPy. So we can create a matrix, so a vector inside first of all. So we can create, just to show you a different operation, we can create, first of all, a vector of random numbers, which is obtained by using randint of random. So we can create 20 elements that goes from 0 to 50 in this way. So this means that you are creating 20 elements that goes randomly, that can be chosen randomly from 0 to 50. So you can print, okay, you have 20 elements, and you can reshape these elements in a matrix that has 5 rows and 4 columns. Of course, 5 for 4 is 20. So we have we have just a reshape of this vector in a matrix. But you can have the same commands just using, for instance, a reshape here. So we can remove this command here. So it is the same. It's just something like a nested operation, in which you are taking this operation on the. So you first create the vector, and then you take the reshape in a matrix. So once we have our matrix, we can create another matrix B that need to have the same dimension, the same size of A. So 5 rows and 4 columns. So we can write B as, and B we can use, for instance, range. So we can use a numbered, a sequence of ordered elements that goes from 0 to 20. And we can reshape in our size. So I just created the number here, and I store it in a vector, and then I can reshape the vector. So just some random way to, some trivial way to build any matrix. And this is our matrix B. We have 2 matrices. We can take the addition of matrices in a very trivial way. So A plus B, and you can print C. And you can see that you have the element-wise addition. So 19 plus 2 is equal to 21. 2 plus 3 is equal to 5. So this kind of operation is called element-wise operation. But of course, for addition, we have only this possibility. And the same is for subtraction. So it is there is no need of telling you how to take the subtraction, but it is the same. You can have two different ways of taking multiplications, of course. If you have any experience with other kinds of programming languages, but also with math, you can see that multiplication of matrices can be, you have the classic multiplication, which is the scalar product or dot product, or you have the element-wise multiplication, in which you are going to take the multiplication of each element of the matrix for the corresponding one of the other matrix. This multiplication in math is called the Hadamard product, and we can write the element-wise multiplication, the Hadamard product multiplication, just by writing A star B. So if you take the multiplication in this way, so you are taking the multiplication element-wise. So you are taking the multiplication, for instance, 44 multiplied by 1, and you take 44. And so on. You take 19 multiplied by 2, and you take 38. So you have the element-wise multiplication. So when you use this symbol, so the star symbol for multiplication between two matrices, you are taking the element-wise multiplication, or also called the Hadamard product. And it is very important because you need to not confuse with the scalar product. And this kind of operation, of course, can be done also for tensors. So, for instance, you can both the addition and the multiplication. For instance, if you take a constant 2, a scalar value 2, we can write the same tensor of before, which is 2, 3, and 4. And you can have element-wise operation, like this one. So you take the matrix X and you are adding the constant 2 to each element of the matrix, or each matrix. Or you can also take the multiplication, the element-wise multiplication of a tensor for one scalar value. You can also take the reshape, or you can also look at the shape of this. Of this operation, and you can see that the shape is the same of the original of the X tensor. So the element-wise operations are very simple and very easy to manage. You just need to pay attention. So for the addition, there is no problem. You just need to pay attention to the element-wise multiplication, and you not need to confuse with the dot product. So the dot product is one of the most fundamental operation, or it is called the scalar product. So you given two element two vectors. The dot product is the sum over the products of the elements at the same position. So it is a standard product between vectors and matrices. I would like to show, I don't know if we have, okay, we can see here what is the dot product. So the dot product is defined in this way. It is the classic operation, the classic product between vectors. The inner product or scalar product or dot product is the same. So you are summing over the products of the elements at the same position. And you can have also some geometrical interpretation of the inner product. So if you are considering two vectors, so you have the scalar product as the geometric representation. So if you consider one vector as the path that goes from the origin to one point, and another vector, a graphical interpretation of this product is by considering the angle between the two vectors. So it provides, it is very important, the graphical interpretation. We can look at something more in detail probably later in this course, since it provides some structure that can be seen as a similarity between two vectors. So if you take the scalar product, the dot product between two vectors, and you have, for instance, a result that is positive, you can say that both the vectors are looking at the same direction. Otherwise, if the product is negative, you can say that the two vectors are pointing to opposite direction. If you look at, if the result of your product is 0, is very important, because you are saying that your vectors are orthogonal to each other. And it is very important because when you we saw that vectors are always referred to signals, to one-dimensional signals. And in many problems of signal processing, you need to have the independence of two signals, the statistical independence of two signals. And one of the way in order to look at onto these properties, to look at their orthogonality. So if you want to see that two signals are orthogonal and independent, you need to see that their product is equal to 0. So from this kind of geometrical interpretation, you can take some advanced properties about signals. So it is very important that when you think to vectors, you can think to signals, one-dimensional signals, and so every kind of properties that are referred to vectors can be transposed to signals. And we will see some example later in the course, but of course we can have it is very important to have some basic notion about this. And we can go back and okay, we can go back to Python, and I would like to show you how to implement the dot product. First of all, let us consider two vectors. So we can consider a vector, generic vector of dimension 4. And another vector, I don't know, consisting of all ones. So I would like to show you x, y, and the dot product x and y. We have x and y, and we want to compute the dot product between the two vectors. So please note that the vectors must have the same dimensionality, otherwise you can incur in some broadcasting. So if you remember from the first lab session, broadcasting is you are filling to zero the structure with less elements. So how to create how to perform the dot product with the symbol dot of NumPy. So the function dot of NumPy, and the dot product. So the dot product, as I said, is the sum over the product of the elements at the same position. What does it mean? That it can be written alternatively as the sum of the element-wise product of all the elements of the two vectors. And here, in this case, we can have the same result. So the dot product is nothing that this operation. So you take the element-wise operation between each element of the product, and then you can sum together. And this is a simple vector-to-vector dot product. You can have also a matrix vector product. If, for instance, one of the two structure is a matrix. Of course, we can use one of the previous matrices, for instance, matrix A, which is 5 rows and 4 columns, okay? And we have the vector X, so we can take the multiplication, the dot product between the matrix A and the vector X. So please note that the vector X has the same number of elements of the columns of A. So of course you need to have when you take the matrix vector or any matrix product, any dot product between two elements, the rows, the number of columns of the first element must be equal to the number of rows of the second element. So the number of rows of the first must be equal to, no, the number of the columns of the first object must be equal to the number of rows of the second object. And this is a very trivial operation. So once you understand what is this kind of operation, it is very trivial to manage about this operation. So alternatively, in the same way, you can have the matrix product. So for instance, if you have we can consider a dot product between the matrix A and a matrix. So the previous matrix B has the shape 5.54. So we can consider another matrix which is once. And we can define the shape as 4 3. This is a different way of writing the same thing. So I have created a matrix with all ones. So I try to use different kind of commands in order to let you know a different way of writing special matrices or other things. But please look when you look at your notebook. Try to understand every simple way to write these commands. We can have the dot product. So now we have that the shape is 4, 3. So we can have the dot product between two matrices. The matrix A, which is 5, 4, 5 rows and 4 columns. We have that the matrix B has the same number of rows of the number of columns of A. So we can perform the dot product between A and B and having a correct result. So I think that is very, so for now, I think that we spent even much time about product and so on. So, but I would like to take some time because it is an opportunity also to take practice with. So I would like to introduce other kinds of things. So yesterday we saw how to perform a transposition of a matrix just to flip the order of rows and columns. And so here on the slides you can find all the theory associated. So I showed yesterday how to transpose a matrix. So does it mean that you are rotating an image? So you are just flipping the number of rows and columns. And the Hermitian matrix, of course, is the conjugate transpose, complex conjugate transpose of a matrix. If you have a complex number, for instance, the symbol is the Hermitian. In Python, this is not in Python. We saw yesterday that we can take the transposition of a matrix just by using the command .t, of course, but unfortunately we don't have the command .h for the Hermitian matrix, so we need to take this command like a.conj.transpose, or I mostly use this command, which is a.conj.t. So first you take the conjugate. Complex conjugate of the elements, and then you take the transposition. It's a little bit complicated, but of course you just need to remember this passage. But you can find a lot of documentation on the website, on the web. So we saw that you can take some slicing here inside the rows, inside matrices, to select rows and columns. Of course, if you want to take a look, you can have the same thing that we saw in the lab sessions, even in the first lab sessions. So reshaping matrices, we saw how to reshape matrices. The diagonal matrix, of course, we will see some example how to take diagonal matrix. So the diag operator is something. So taking a vector, it returns a matrix whose diagonal is a vector, and the other elements are 0. But you take also the inverse of the diagonal. So taking a matrix, you can return a vector whose elements are on the main diagonal of the matrix. We can have, it is not, I don't want to boring you to implement everything in Python. I think that it is important that you understand the basic things, that step by step, as we encounter some new notion, we can implement and use it. But you can find everything on these slides, just some basic summary of the notion and also the commands in Python. So when we will use the trace of a matrix, we will also come back to these commands, and same for the triplets matrix. So one of the things that is important is the inverse of a matrix, because in a lot of algorithms, mostly in signal processing, but also in machine learning, we need to take some operation that requires the inverse of a matrix. And it is very important because the inverse of a matrix is a non-trivial operation, and it may cause a lot of problems if it is not performed in the right situation, in a proper way. So if we consider a square matrix is said as invertible or non-singular if we can find a matrix B, a square matrix B, such that the multiplication of B by A is equal to the identity matrix. So the identity matrix is a matrix which has all ones on the main diagonal and a zero on the other elements. So in such a way, so the matrix B is determined from A by using the inverse of A, which is denoted by A to the minus 1. So A to the minus 1 multiplied by A is equal to the identity matrix. How to perform the inverse of a matrix in Python? By using this command of numpy. So you can call linal from numpy and using the function inv if you want to just having the inverse of a matrix. But we will see some further examples. Some very useful properties of matrices is the solution of problems like this one, which we will show a lot of examples later in this course, but I would like to give you just a brief view of this kind of property. So if A is non-singular, we can have the system, this kind of system equation. So consider that you have your matrix A and a vector B. You want to know what is the solution of X. So it is just a vector representation of a system of equations in which you have a matrix of coefficients X, which are your variable to be solved, and B, which are the known terms that you have. So imagine that you have a system of equation. You can write it in a compact form, just using a coefficient matrix, a vector containing all your variables to be known, and a vector containing the known terms. So how to solve this system of equation? You need just to solve this system of equation just by putting it on the other side. So just by taking the inversion of the matrix A. So how to implement this in Python? Just to use the solution, the function solve of linalg. And here we have B, which is a lowercase letter b. So you can use Linux of is A is a square matrix. Otherwise, you have this other function, but we will come back later on this kind of operation. When you don't have a square matrix, so imagine that your matrix A is rectangular, is a rectangular matrix. Of course, you cannot have the inverse of the matrix, but you need to have the Moore-Penrose pseudo-inverse. How to compute the pseudo-inverse? So this is a general solution of a pseudo-inverse. So if you have a square matrix, of course, it is the same of having the inverse. If you don't have, if you have a fat matrix, so the number of rows is inferior than the number of columns, so you have a fat matrix, so it is a large matrix. You can compute the inverse in this way. So you can take the Hermitian of matrix A multiplied by A multiplied by H multiplied by the transposition, the conjugate transposition of A to the -1. Otherwise, if you have a tall matrix, so the number of rows is larger than the number of columns, so a tall matrix, you have the other way, so this matrix is put on the other side. And you have a general way to write this pseudo matrix just in this way. So you can take this symbol in order to, the hash symbol, in order to represent the pseudo matrix. So with the pseudo matrix, so a pseudo inverse matrix, you can represent any kind of inversion of a matrix depending on their size. So it is very important to think always at the size of the matrix when you need to deal with inversion of the matrix. I don't want to bore you a lot with this kind of operation, but it is an operation that you will find a lot of times in your algorithms, and we will take some example in a few minutes on Python. So here you can find a lot of other things, geometrical properties and other things. Then I will show you how to project a matrix. So I can just give you now some information about how to project a matrix. So and then we can have an example of the projection with signals. So we consider a square matrix P. It can be called a projection operator if the square root of P is equal to P. So it is idempotent. So in every elevation to to a number of this matrix is always equal to the same matrix. So P has a lot of the properties. So if P is symmetric, the projection is orthogonal. If P is a projection, also the difference between the identity matrix is a projection matrix. We can, examples of orthogonal projection are matrices associated with a pseudo-inverse in over and under determinate case. Over and under determinate case is just the case in which you have a fat matrix or a tall matrix. It refers to the case of the system of equations. So in overdetermined case, also when you have a tall matrix, you can write the projection operator as the pseudo inverse written in the way that we saw before. So, okay, so if you remember this case, all these cases, the the overdetermined case is the case in which we have a tall matrix. So here is the pseudo inverse, and if we want to project a vector, we can multiply it by A. So A multiplied by the same, so the pseudo inverse of A. And we can also find the complement, the orthogonal complement projection, which is the difference from the identity matrix. I will show you later an example of projection. So it is very important to understand what is a projection. But this is the case of underdetermined case in which you have the pseudo inverse, which is the other case, or the fat case, and it is a graphical representation of orthogonal projection. So I will come back later in Python to show you what is the importance of a projection, because you have a matrix over a vector and you want to project it. How does it mean? So if you have a projector operator P, you want to take a vector and you want to take the projection of this vector on another space, or in another space. So I will show you an example of projection with audio signals directly by showing you in Python, but here you can find some slides. So before taking these advanced examples, I would like to show you some other basic knowledge. So then we can move to other more advanced examples. I would like just to very briefly introduce what are the norms. So the norms are very important because in machine learning, we use a lot of the norms of a vector, because the norm is an operator and it is one of the most natural ways to define or measure the distance in a metric space. So we can, of course, we have two vectors and we want to measure, we have 2 points and we want to measure the distance between 2 points. So we can use the norm of vectors to take lots of operations. We can refer to the norms as a length with respect to a vector space. So depending on the metric space that we consider, we can have different distances. In the case of normed space of order P, we can, a generic norm is the definition of LP norm. So P is the order of the metric space that we are going to consider, and L is the distance, or the norm that defines the distance between two vectors in that kind of metric space. So we can have, this is a general norm of a vector of order P. We can also, have a lot of norms, and we can, one of the most used norms are the L0 norm, which is just by the, it is a kind of measure that returns the numerosity of non-zero elements, so the number of non-zero entries of a vector. So if we apply the L0 norm to a vector, the output is just the number of elements of that vector that is non-zero. So we can have also the L1 norm, and which is just the sum of the absolute values of the element of a vector. We can have the definition of the infinite norm of a vector, which returns the maximum number of any absolute value of that vector. One of the most used norm, of course, is the L2 vector norm, which is defined as, which is also known as the Euclidean norm. So we can just take the distance between, it is always used to measure the distance between 2 points. So it is a very, I think that all of you has knowledge about the Euclidean norm. So based on this norm, we can define a lot of distance measures. Why they are so important, distance measure? Because imagine that you have, so we saw in one of the previous lesson the example of classification when you have some points and you need to have two representation of points, two groups of points that we call clusters. So if you have different groups of points, if you remember the example of the iris flowers, in which when you take at the features of any image, you can see a representation of points. So these are called clusters of features. When you have a new point, you can measure the distance of this point between the cluster, for instance, the center of the cluster, or the other way, another point of that cluster, and so on. So there are different approaches. So in order to measure the distance between a new point from a cluster, you need to define a distance measure, and all these measures are based on norms. So it is very useful that you are comfortable with this kind of notation of norms. But I will come back later, of course, on this kind of notation in order to define something more in a deeper way. So it can be just boring for now, but just to show you that when you have the norm, you may think to writing to measure some distance from 2 points in a metric space. Why in a metric space? Because you can have different kind of spaces. If you consider, for instance, the features, a particular feature space. So I would like just to briefly show you how to write the norms in Python, but it is very simple. So I would like to write something about norms, and then we can move on. So briefly, I would like to introduce one of the most used norm, which is the L2 norm, so the Euclidean norm, which in machine learning is very used because we can find in a lot of operation. So if you can define a vector of 2 elements, you can compute the norm of this vector as just by using the command linalg. So it is just a routine containing some function of linear algebra, and just taking the norm with the default value, and the result is 5. The result is the result of this operation. So you take the square or the square of each element, the absolute value of each element. You take the sum and the square root of the result, and you take the sum of the square of these 2 elements and take the square root. So you can also take the norm of matrices. So you can, I don't know, generate a matrix just by taking, I don't know, So we can generate a vector like this one. It goes from -4 to 4, and a matrix B, which can shape using the same elements of A. So I reshape 3, 3. So we can compute every kind of norms just by using the command norm on a vector, and the same on matrices. So we can write np linalg dot norm of A and B. So for A, we just see an example. We can see the same from B. And this is the norm of the values of the matrix P. But we can also use the L1 norm. So the L1 norm expresses as the sum of the absolute values of the actors, the elements of the vector. In machine learning, it is also often used because with respect to the L2 norm, the L1 norm is less influenced by outliers. What are the outliers? Are those values that are very different with respect in the magnitude values with respect to the other elements. So imagine that you have all the elements that are comprises between I don't know, a range 0 and 1. Then you have an element that goes to 10, for instance. So it is a great difference between one element and the other ones. So that element is called an outlier. And when you have an outlier that can affect a lot the results of a norm, L2 norm, while the L1 norm is less influenced by the outliers. And in Python, we can just have the command np linalg norm just by taking this kind of expression, but it is the same of taking the absolute value of A and then just take the sum of all the elements and you take the same results. So it is the same. So you can have lots of other norms, but it is, I can send you some kind of other examples just by simply changing the order of the norm inside here. You can have norm order 2, which is the default. You can have other kind of norms. You can have the Frobenius norm if you write in this way, or you can have lots of other options. You can have the infinite norm just by writing in this way. So you can take some different examples. You can take some practice just by writing some examples like this one. I would like to move to an advanced, some advanced examples. Since I would like to show you something that is related to signals and look how to use all the elements that I have introduced applied to signal. So especially to signal processing applications. So I would like to show you an example with an audio signal and an example with images. And for instance, so we start with the audio signal examples. I would like to, so we can write here a new, you can start a new argument. So before introducing So, okay, I can just introduce the problem, and then I would like to give you some further information about the notion that I'm going to introduce. So the problem that I'm going to show you is this example. So we want to consider an audio signal which is a gong sound. So a gong sound, so imagine that you have the gong is a grid plate in which you can put um, your uh, your strike strike on this gong, and you take a sound which is very great in the initial part, and then it goes to decay as the time goes on. So it is a graphical representation of the gong, and it is the frequency content of the gong. So you have in yellow the most energy, which is comprised in a lot of frequency. So here you have the frequency of the, I can come back later on this kind of representation, but here you have the frequency content of the gong. So you can see that you have a lot of frequency that are comprises between in this sound. So it is the time representation of the waveform of the gong signal. And then you have the spectral content, so the frequency that it is going to sound. So we consider this audio signal and a musical note A. So I don't know if you have if you have experience with musical notes, but the musical notes A is in Italian is the note La. So in the British notation, you have the musical notes that are A, B, C, D, E, and in Italian we have Do, Re, Mi, Fa, Sol, La, Si. And we have the same representation, but with in the British Anglo-Saxon notation, the musical note A is equivalent to the note La in Italian. So we want to, so every musical note is referred to a particular range of frequency. In particular, the musical note A is has a spectral content related to the frequency at 440 hertz. So it is just one frequency, one specific frequency. And we want to know how much of the note A is contained in the gong. So a musical note A is a kind of signal in which the spectral content is very defined. And we want to know how much of this musical note is contained in that signal. So we want just to answer this question just by using some linear algebra operation. So what is the solution of this kind of question? Is that we want to project the original signal into the musical note A. So we take this signal and we want to project. So of course, this signal is nothing but a vector. So if you have a vector, you can use linear algebra operations on vectors. So we want to project the vector related to this signal into the musical note A. So we are projecting a signal in another space and we take a transformation of that signal. So in order to take this operation, we need to represent the signal and the musical note in the frequency domain by applying the short-time Fourier transform. So it is important to introduce the short-time Fourier transform because we will use it in a lot of analysis in machine learning when we deal with audio signals. So when we need to analyze, to take some kind of processing with audio signals, basically a lot of machine learning operation, machine learning algorithms refers to the short-time Fourier transformation. So it is very important that you have some brief view of what is a short-time Fourier transformation. So it is something I think that all of you have had some experience with Fourier transform. So all of you have some knowledge about Fourier transform. I don't want to give a lot of recall also about this kind of things, but probably the short-term Fourier transform. So probably I don't know if any of you have had some experience with short-term Fourier transform, but it is very trivial as a concept. So why we use the short-term Fourier transform? Because we are probably interested to understand how a signal and its main features varies in the time frequency domain. So we want to have a visualization of how a signal change both in time and in frequency. So what does it mean? So that we want to see how this signal changes in time and also in the spectral content, so in its spectral content. So the Fourier transform, as you should know, of course, the Fourier transform does not have any temporal dependence. So if you take the Fourier transformation of a signal, you have just the complete view of that signal, but you have not a temporal dependence. So if you want to see how how a signal is changing its spectral content in time, you need another instrument. So the Fourier transform is not completely satisfying because it just gives you a complete view of all the signal, but instead we need to have some analysis of the spectral content, which is also related to the time, so to the temporal behavior of that signal. So one of the methods to have a time frequency analysis is to consider this short-term Fourier transform. So it is just so it consists in dividing a signal. So you take a signal and you can divide a signal into a number of frames. So you take a signal, probably in the next session, I will have some graphical tools to have a graphical blackboard in order to project something also on the screen. So imagine that you have a signal, you divide this signal in frames, and you take the analysis of the content of the spectral content of each frame in order to have a view of how it is changing in time. So for each frame, you take the Fourier transformation, and then you take all the slices on the results of the Fourier transform that can be collected in order to give you the representation of the time frequency analysis of that signal. So you can stack each Fourier transform of each frame in order to obtain the short-term Fourier transform. So with reference to linear algebra, you can think that a signal and all the frames of the signals can be represented by vectors. So the Fourier transform of each frame is a matrix in which you can see the frequency bins times the frequency bins and the samples like this one. So here you have the short time. So here you have the Fourier transform of a frame of a signal. So you have time. It is nothing but a matrix in which you can find the time related to the frame, which is a short time with respect to the whole signal. And you have the spectral content, so you have the frequency beam, so the values of each frequency of the scale that you are considering. So for each frame, you have a matrix that represents the spectral content. So a matrix that in which you have samples as rows and frequency bins per columns. And it shows the time frequency content. Since you have a lot of frames, you need to collect a lot of these matrices in a tensor. So you have a lot of matrices like this one that are stacked in a tensor. So you have a tensor in which you have the temporal variation of your frequency time content. So I will show you this kind of transformation. We can talk more about short-time Fourier transform later when we can have also other kinds of examples. So in machine learning, we can also use spectrogram, which is nothing but the squared magnitude of the results of the Fourier transform for each frame, in which you can have just the squared magnitude. So you are looking at the energy of the spectral content for each frame. So in machine learning, spectrograms are often used also to apply image processing methods to audio signals instead of traditional audio signal processing methods. We will have lots of examples in the last part of this course in which we will use neural net, some kind of deep learning methods that are applied to image classification, for instance, convolutional neural networks. I think that it is a kind of method that is on the mouth of everyone now. So it is one of the most known method of deep learning that we will going to study in the last part of this course. And for instance, you can use this kind of methods on audio signals just by transforming the audio signals in just to have the spectrogram representation. So you have an image representation of your audio signal, and then you can apply some image processing, some machine learning methods related to image processing, also to this kind of transformation of audio signals. So it is very often used, and we use a lot in a lot of in some projects, in lots of projects that deals with audio signal. You will have some kind of similar transformation. So the thing is, in order to solve this problem, we take the gong signal, we transform it in a short-time Fourier transform. So we take so we transform a signal X in a matrix. And once we have the matrix, we can compute the projection of that matrix just by taking the properties of the pseudo-inverse and the projection. So if the A is the short-time Fourier transform of the gong signal, we can create the projection operator of A and apply this operator to the signal x in the frequency domain. So we have the projection of x into p in the frequency domain. Then in order to obtain the results in the time domain, we just need to take the inverse transformation, the inverse of the short-term Fourier transform, which is similar to the inverse of the Fourier transform, but for all the frames, and we need to reconstruct the signal. And we can have just the result, which is just all the part of the gong signal that is related to the musical A. So this is the projection of the gong signal in A. I would like to show you very briefly in Python how to perform this kind of operation. So I would like to move to Python so we can import all the libraries. So we have NumPy imported, matplotlib. I have imported also matplotlib to plot the signal. So we need to import, as we saw yesterday, we need to import the IO submodules of SciPy. So in order to load the wave file, we need to import from scipy.io. We import wave file. So we need to import the gong signal from the folder data. So in the folder data, you have the gong signal .wave. So in order to import the signal, as we saw yesterday, we import the signal in this way just by using wavefile.read, and we import the gong signal, the gong.wave file. So remember that in this case, you are storing the signal, your signal in a vector x, and fs is just the variable in which it is stored the sampling frequency of the audio file. So in this case, the sampling frequency of this file is this one. So at least 8 kilohertz, mostly 8 kilohertz. And we can have that. We can also measure the length of the signal, which is the length of the vector, of course, in terms of number of samples. So we have this number of samples for the signal. If we want to know, we can also take the signal length in time. So we can build the temporal axis for our vector. So we can create our axis of samples, and we can divide it by the sampling frequency. So we have that simply, we can say that we have the, if we have the division of the length in samples divided by the sampling frequency, we have the time. So 5 seconds of signals of our gong file. So we can normalize our input in order to have our value comprises between -1 and 1. So we take the division of all the elements of our vector. By the maximum value of the vector. So in this case, we have a normalization of the input. So the maximum value is equal to 1 or -1. And we can have, for instance, a plot of this waveform just by using the Python, the pyplot library. So we have, we can write the title, so we can write audio waveform of long. And we can plot the signal X and show it using LT show. But something is not working as I want to. I had some problem in Python 2 with this operation, but I don't know why, but definitely in Python 3, I'm sure that it works in Python 3. So if you take this operation, you will find the same plot, but with a scale comprises between 1 and -1. So if you have Python 3, you will have the same, if you take the normalization, you have the same results, but taking this picture between -1 and 1, not between this larger scale. And we can compute now the short-term Fourier transform of and plot the spectrogram of the signal. So we can import the SciPy. I don't remember if I have imported SciPy. So I can write here from SciPy. I can import signal. So look at, if I include another cell here, you have the ordered number of the execution of the cells on the left side. So it is very easy to understand what is the number of the order of the operation that you made. So once you import the signal submodules of SciPy, we can compute the short-term Fourier transform very easily, just applying just apply the function which is signal.stft. So signal STFT, we have that the function can be written in this way. So so you have the spectral content, the time content, X, which is the transformation of the signal, the frequency domain. STFT is the function. X is the signal that we want to analyze. Fs is the sampling frequency. So we need to write the n per seg, which is nothing but the number of the number of points that we need to consider for each frame, and we can write it as a blend. So blend is we can write this as the window length for each segment. So once you divided the signal in frames, you need to have some overlap from one frame for another one. So you need to, because of the reconstruction of the signal must be continuous. And so you can have some kind of windowing function between any kind of frame, any frames, subsequtive frames in order to have the right reconstruction of the signal. Otherwise, you will listen to some clip between a frame and the other one. So in order to reconstruct the signal exactly, you need to take some windowing of the frames, and you need to consider some window length, which is the length of the window, so of the overlap, the length of the window that you are considered from the frame, and the length of the overlap, which can be considered as the as a part of the window length, so the frame length. So you can consider just a part of this frame is overlapping between a frame and another one. So it is not easy without the blackboard, but I hope that in the next week I will have some more instruments to take better visualization of this kind of operation using online lessons. So we need to write the number of overlap samples, which is equal to h, and the number of FFT points, so the number of points of the FFT transformation. So by default, if we write known, we are taking that number of the frequency point is equal to the number of the samples of the frame. So I hope all it is correct. Okay, it works. So in this object, we have the representation of the short time Fourier for that signal. So we have this matrix, and we can consider, we can plot the spectrogram of this matrix. So we can plot the spectrogram of this matrix, so we can consider using the function spectrogram. I will I will explain every. These are the output variables of the function spectrogram, in which we put the x, which is the signal, the number of points, everything. So it is very similar to the short-term Fourier transform, but it just directly plot the spectrogram. And it is used just to plot this is the content, this is the frequency, the frequency beats that you are, the frequency range that you are considering. These are the number of beats, and this is the image that you are going to consider. So in order to plot the spectrogram, you just need to write the title. You can write the title, for instance, spectrogram. You can plot, I don't know, the label, for instance. In this case, you will have frequency on the y-axis, and time on the x-axis. And you want to show, okay, I take some error here. Because it is not spectrogram, but is spectrum, if I remember well. Okay, it works. So it is the representation of the spectrogram, but it is nothing but the squared magnitude of the short time Fourier transform. So here we have the time, so we have 5 seconds of our signal, and it is the frequency content. So if you can see, we have the frequency content that vary over time. So we can have frequency content at any kind of frequency from 0 to 4 kilohertz. So I can show you how to generate now. Now we can generate the musical note A and take the similar operation to the musical note A. So we can see that the frequency of the musical note is 440 hertz. So the musical note A is just a sign here of the frequency 440. So how to generate the musical note A is just a sign. So we can use NP sign, and we can just take the sign of the frequency of the musical note A multiplied by the time axis that I built. So the same time axis of the gong signal. So I can also plot, so PLT plot A, but of course in this case the plot is just a sign with a higher frequency, so the plot will be not clear enough, I think. Okay, so you can see something more like I don't know, I think you can have something like this. I need to check a little bit. Okay, so I can compute the short time Fourier transform even for this kind of, so it does not sense to show you the plot of the note A. So I would like to compute the short time Fourier transform from the note A in the similar way of before. So we can cut and paste the same function and just change the variables here. Okay, and we can also plot the spectrogram. to show you how to project, so how to build the projection, like so just to repeat these equations. How to repeat this equation, I will go very quickly so I can show you. So the projection matrix can, so I would like to, if you have the, as a first thing, I create the dot product between, I create the dot product between A, Hermitian A of A and the matrix A. So the Hermitian can be written as the conjugate of all the elements and the transposition of all the elements of A and A. So I'm writing just this operation here. Then I take the inverse. So I take this operation, so the inverse of this object, so the inverse of AA, which is NP linalg, as I showed you before, the inverse of AA, just by using the linear algebra function that we showed you before. Then I need to take this product between A and this object. So I take another dot product between I don't know how to write it. So NP dot A and this previous object. So I'm writing too many of these A and I. So the operator finally is the product between this object and the transposition, the complex conjugate transposition of this matrix A. So finally, P is the NP dot multiplication between this and the transposition, the Hermitian transposition of A. So once we perform the matrix P, which is the projection operator, we just need to perform the dot product between the projection and the short-term Fourier transform of X. So it is very simple just to write the dot product between P and X, and you take the results. I did not launch because the previous errors. Then you just need to have, so we need the projection, but in the frequency domain, we need to take the inverse of the short-time Fourier transform in order to have the time frequency, the time representation, just to have ES, EFT, Q, and FS. So here is the command to have the transformation from the frequency domain to the time domain, and then you can plot this this signal just by having a PLT plot of U, and you should have the same result as this one. I will send you the complete notebooking which is working. So if you take also the plot of the spectrogram of this PLT, if you just take the PLT dot spectrum of U, if you and take PLT show, you will have also the spectrogram of this signal U. And you will say, of course, you should have different, so you have the frequency on the y-axis and time on the x-axis, but you will see the fact that you will have only the frequency on the frequency 440. So you just took the projection of the gong in the A signal. So what does it mean? That you are removing from the gong signal every kind of signal, every kind of content that is not related to A. So I am removing from the gong signal every part of the signal which is not related to this frequency content of the A musical note. So I hope it is clear, but we will have lots of other examples like this one. I will send you the complete notebook of this examples, so in order to have a complete view. And I also insert some other comments in the example, so you have a clear view of every kind of operations. Okay, so see you, bye guys. See you next week.